Cool. Questions on homework 4 due today? Oh, good. Yeah, feel free to play around with FFT because technically, I think homework 4 is not about FFT itself. It's more about array, um, you processing. Um, but I guess also think about your midterm assignment. The instruction is up here. Anyway, open-ended. You only need to do 2 of D3s. Usually people choose the first 2. But if you want to explore classes and objects, of course, that would be great. Technically, if you improve something from sound, you are sort of exploring class and objects. So anyway, yeah, so sound library will likely be the main part that you will need. Analysis, there's a bunch of things: amplitude, beat detection, FFT, pitch detection, waveform. But you could also think about some of the other things we talk about in class to incorporate that in your music visualizer. And on top of that, live demo, it will be on the day after the fall break. That would be October 15th. Yeah, so be in person, talk about how you design your music visualizer, 5 minutes each, so that we won't go over time. What's the concept of your design? How did you implement your desired features? Some more the technical part. What's the most challenging part? What's something you like to add or simplify if given more time? So, basically just cover these and show what you've done. And the project itself will be due on the same day, at midnight. Cool. So start thinking about it and hopefully also get started working on it. Questions on midterm assignment? Just open-ended. So, whatever you like, whatever you think that's cool in class, grab it or something, you see somewhere. Cool. Yeah, so again, homework 4 is due today. Midterm assignment will be due next Wednesday. Cool. Yeah, just a quick recap. Last week we basically talked about all the transformation thing and 3D graphics thing. So technically that's not a must to do it in processing. You just a whole new framework of doing stuff. And transformation is the key of doing anything with 3D, even though we didn't explore it a lot, but that sort of give you like a new perspective of doing stuff. So basically transformation is about transforming the axis, the grading system, rather than, specifying exactly where stuff should be at. So, if you look at this rotated square thing, if you want to turn this, square into that position, instead of just like trying to get all these, points on the original axis, can you sort of like think out of the box, try to translate the axis and turn the axis, rotate the axis, and now you start, drawing your square out. So the same thing can apply to, mirroring an image. In this case, mirroring this pool image, but also, when you have a webcam, how do you mirror it? So you can also do, scale -1, so that you turn this axis the opposite way on the x-axis. So now everything flipped, but now you have to move stuff onto the canvas where you are showing stuff. And we talk about, reset metrics, where reset to the original identity metrics, but also there's like push metrics and pop metrics, where there's a metric stack already implemented in processing, where you can push stuff into that and then grab stuff from that. So that will become handy, but it's first in, last out. And we talk a little bit about what's the difference between stack and quick queue. Stack is first in, last out. Queue is first in, first out. But I guess the easier way is like, this is stack. So whatever you put in the first, it will be the last when you pull out. And Q would be more like a cup dispenser where you put stuff on the top, you grab first. The first one you put into it, it will be the first one coming out. And we talk about all the 3D things, and everything is 3D. We only have, processing, we only have box and sphere. Everything else, you have to try to use transformation to do it. So in this case, translate, rotate Y. Now you have different axes to rotate around. So you have to do rotate X, rotate Y, rotate Z. But basically, when you do this size, you do P3D at the last one, then it will turn this canvas into a 3D mode. You can also do sphere. We talk about it. We need to think about the light. If you turn off the light, it will become 2D. And you also need to think about the perspective. So by default, in processing 3D mode, everything will be this perspective mode where you have to define the light, where you also need to define where you are looking at it. By default, there are some, preset position, but you can also play with it to create some cool effects. We didn't explore a lot, but that's how 3D works in processing. So perspective, meaning that, distance matters. The closer you are to the object, the bigger it looks. You can also set up this ortho mode, where sometimes it could be fun to work in that mode. For lights, there's a bunch of different lights, ambient lights, directional light, spotlight, point light, should be quite self-explaining. Anyway, we could use directional light to create this creepy eyes 3D version. Basically, is that you want to, have the directional light from the mouse that you have all the way, throw it to the ball that you have. And that's it. That's what we cover in 3D. Quite limited, but there's a bunch more you can explore, but that's not the main focus of this course. Questions on 3D? Why 3D? Yeah, there are some like cool stuff you can do. So mostly, at the end it's still 2D, but think about gaming, scene could be in 3D and then you walk around. So, mostly still a projection onto the 2D space, unless you are doing some VR stuff. But for processing, that's sort of a way to think about 3D in the 2D, canvas. Cool. Today we will talk about motion in physics. Basically making your stuff that move more like in real life, things will collide. There could be gravity, there could be other forces, but particle systems, but basically make things more realistic, kind of. So previously we talked about the bouncing balls things. You can have an object and then create a bunch of bouncing balls, but they won't collide to one another. But in this module, we would just look into, how motion and physics work. Cool. Let me grab the slide. Cool. So motion and physics. So the first thing we would talk about is acceleration. So acceleration, think about it like, how you move the stuff. Moving the stuff is basically apply that velocity to a moving object, right? So we typically just do something like x plus equals speed so that the things would just keep moving on. So acceleration is sort of the same. Now acceleration is just, speed plus equal acceleration, right? So that's basically what we can do. But think about it a little be further, how you would define this gravity. So now you can basically just do speed y plus equal gravity. So the original speed y would be point upward when you start the ball, when you when you drop it. So original speed y would be very small, and then you apply gravity, apply gravity, apply gravity. So now it moved faster and faster until it hit the bottom, the wall. And now, once it hit the bottom wall, it will just turn the opposite way. and you will need to apply a decay so that this ball will stop jumping. So the decay will basically be sort of a thing about like the energy, the waste of energy when you hit the bottom wall. If you don't apply this decay, the ball will just jump to the original height. I think I have something to show. Maybe find examples. Cool. So, if you look at this thing, it's not that tricky. The speed would now be plus equal gravity, but still when you do the y position, it's just y plus equal speed. So basically now things become, second order, where you have, x, y actually, y equals plus equal speed y, but now the speed y will also increase over time. Speed y plus equal gravity. So these two things basically just model that, second order acceleration. Cool. Well, I don't think that's what I'm looking for. Gravity. Where's gravity? Okay, found it. Cool. So this is what we are looking at. You have a ball and you just apply gravity and then you move the ball and you check if it hit the wall. And if you go into this class, the definition, random with random position to start with, speed x will be random, like the horizontal speed. When you move it, basically x plus equals speed x, y plus equals speed y. In this case, speed x would stay the same all the time. For speed y, if you apply gravity, speed y plus equal gravity, when you hit the walls, basically just bounce back. So now the interesting part of the speed y is that there is a decay. So so in this case, decay will be 0.95. If we run it, let's see how it goes. Kind of leggy for no reason. Um, anyway, so if we don't have this decay, it will be 1, so no decay, then you will see that wherever it starts with, it would bounce back to the original part. So it will never just, stop bouncing. If we get a, larger decay, 0.9, so 10% of energy will be wasted. So it will be, bounce back, not that further away. If it would be 0.5, then it would jump to the half, not even half, like quarter of that. And it would just stop jumping right away. So basically this decay just determine how much energy was wasted in that case. Actually how much portion of that speed is gone. So that's gravity. So you can just mimic gravity to apply that, and you can actually just reverse that gravity by doing it the opposite way. So you apply gravity as y acceleration, and you reduce the speed a little bit when it hits the bottom wall, so that it will make it more, realistic. So you can also do upside down gravity. Basically now you just turn it the other way, minus equal gravity, and now when it hit the upper part, it will be, that thing. But to be honest, this is not upside down gravity. So this is basically if you have a balloon or something that float, this is basically its behavior if it's, lighter than the air. Anyway, you can call it upside down gravity or something, balloon. Cool. So the same idea. But basically, the acceleration idea could be applied to different stuff. So in this case, this is when I have the mouse cursor and just trying to drag this ball all the way toward where you are. So what we are trying to do here is that we will have, location, velocity, acceleration. So location will be sort of like X, Y. So now everything is a P vector because, you want to handle X, Y at the same time. You will have a P vector velocity where the ball is currently moving. You will have the acceleration. So you want to sort of like create a gravity field where the acceleration is just where you are dragging this ball from. So now you can create something like that. It's like a chasing game, kind of. Let me grab it. Okay, let me see how it works first. Cool. So this is what it's like. This is actually one of the processing examples. Oh, it's here. Cool. So, I would drag it all the way towards where my cursor is. So, you will have like its location, its speed, it's moving around, but anytime where your cursor is, you will have a gravity that's, dragging that ball coming toward your cursor, where your cursor is. So it will sort of like chase you, but not exactly, like right away, but it will have some, damping effects. But basically how you want to implement this is basically, you will have a bunch of, location, velocity, but at the end, there will be a force coming, dragging the ball toward the cursor, where the cursor is. So if you look at what's going on, basically, mouse P vector, mouse X and mouse Y, and then you want to calculate the acceleration, then you basically just do mouse minus location to see where that, force vector is. And you set this magnitude into 0.2. So you set a constant force for that. So what's going on here is that you have like mouse X, mouse Y, and you have a ball, and you calculate this vector. So this will be the acceleration vector. And then you do acceleration that set magnitude 0.2. So you force this vector to have the magnitude of 0.2. So you always have this constant dragging force. And you do velocity that add acceleration, and there's a top speed that you want to limit it. And then you do location that add velocity. So this isn't not necessarily a realistic way. So if you think about like a dragging force between two stuff, the force would depends on, the inverse square of the distance. But in this case, we're using a constant force, but it will be more fun. So anyway, there's all sort of things you can do to pretend it to be sort of like dragging stuff, but it's not essentially purely physical based. Cool. A lot of different things you can do, gravity and fluid resistance. So fluid resistance is another thing you can mimic in processing, where basically this drag force by physics law is like the force is, proportional to square of velocity. So if you look at this, everything just come into with the same speed, but because, the force would be the same initially, but F equal ma, so it will be changing the acceleration differently. That's why they will reach at different place. The bigger the mass it is, the quicker it reach the bottom. Anyway, but in this case, you're basically just trying to add these things up. So once you calculate the force, then you calculate the acceleration, apply the acceleration to the velocity, then apply the velocity to the location. So basically, it's just trying to find the force divided by mass, you get the acceleration. So speed plus equal acceleration, location plus equal speed. That's how you get some of these simulation to be done. Cool. I think I also have some of these. This is again one of the example code at processing. So on the processing website, there's actually tons of example code you can explore. Yeah, this is the guide. Cool. So you can actually change the coefficient actually. So the liquid coefficient, if we like make it bigger. Oops. So that's too big. Some of those actually just jump over those. So the coefficient, if we divide it by 10, this will have little effect on the speed, you know. So it will have a less, less sticky, basically. Cool. But basically, if you look at the code, it's just trying to calculate the force, apply force. You want to calculate the force basically. Yeah. So you will have drag. If you are in the liquid, then you apply the drag, apply force drag. Gravity is always be applied. So you apply force on gravity, and then you just update the position, update the speed, update the location. Cool. So basically you are combining multiple forces. That's it. You can also create something like this, purple rain, where you have different drops. And this is very interesting because, this is essentially what we just cover. Just follow its gravity. That's it. Different lengths, random initial velocity. But what's more interesting is that it actually just used this very easy idea, random stroke weight, so that it create this illusion of distance, because that's how you feel the distance, right? The further the raindrop is away, the fainter this thinner it looks. So you can actually create this with just things that we just talked about. Gravity, it's just a tiny bar that just fall over the time. The raindrop will actually become longer. So you don't want to keep the bar as the same length. You want to keep the top of the bar as its own trace and the bottom of the bar another trace. So it will get longer over time. Cool. But basically, that's some ideas, playing with forces, so that you have acceleration applies to the speed, speed applies to the location. Okay, now more fun. Now let's look into collision. This is where things go a little bit tricky. So previously we would talk about, this bouncing balls. We talk about, we have a class, then we can scale it. Now we can have like 10 balls, we can have 50 balls, we can have 100 balls. But the question is that, well, these balls just pass through one another, like, there's no physics involved. So how can we do it? How can we sort of like make it more realistic that balls will collide, not just with the walls, but also with another balls? So, previously we talked about, an array of array of objects, ball classes, a ball class, I guess. And you can initialize all of those, and you can just move, check whether they hit with walls, and you just show it. So the idea of a collision detection, this is what we want. We want to see, we make the ball bigger so that they easily collide. But basically, what else do we need? Um, you know, First, how to check if the ball collides with another. That's not too tricky, right? Take a ball, take all the other balls, just like you are checking whether it hit it hit a wall. Check all the other balls. Do they overlap? Do they, calculate the distance? Are their distance like shorter than their, 2 times their radius? But what kind of function do we need? So basically we need like a check collision function where you look at all the other balls. So this is something like that. You will have an array of ball where these are all the other balls. So for each single ball, you look at all the other objects and you want to for loop over other object and you want to see whether your current ball collide with another one. And if it's collide, then you want to, apply like how they move forward after the collision. So that's basically the idea, an array to store all the other balls, iterate over other balls to check if there's a collision. Once there's a collision, check if there's a collision. If there's a collision, then you want to know where they are heading to next. So now the tricky part is like, how do you handle collisions? So basically, once these two balls collide, you will have a plane. So now it get into more physics, but not too bad. Hopefully, I will persuade you that's not too bad. It's just some calculation. So think about this like a wall. So now once these two collide, now if we only care about the blue ball. So now you can actually imagine this blue ball actually just hit this green ball and it will turn it this way. So they will actually have this like what we call, this is like the normal direction and this is like the tangent direction. But basically you can actually get rid of that ball. You don't really care because once they hit, this sort of like becomes sort of like a tangent plane where you don't really care about the second ball anymore. So what you want to do is that this is your original angle coming in, like your original velocity, and you want to calculate what the new velocity will be like. So that's the essential things what we want to do. So a bunch of math in the next few slides, animations. But basically what we want to do is just to compute what that new angle is. So, the original angle, if we want to calculate it, we need to use arctangent, but this is some, math to get, from the speed y and speed x, how do you get this direction? So, arctangent 2 is basically, whenever you have like a speed x, this is speed y. How do you get this theta? So this arctangent 2 will go from speed y, speed x. It will return this theta for you. So even with a different angle like this, so you have speed x, now speed x will be negative. In this case, speed y is also negative. And once you put speed y and speed x into this function, it will give you this theta. Because again, everything in polar coordinate is start with the right hand side. Oh, actually the other way. Anyway, so you will get the original angle. Now you just do a bunch of calculation. You want to see where this thing is. So how to get that thing? You compute this vector, which is x2 minus x1, y2 minus y1. You get that theta. So basically now you want to do the things. You have the original angle, you have the theta, you have the new angle. These are the three things. You want to compute where that new angle is. So it's just a bunch of maths. So you first turn the original angle plus pi to go the other way around. Now you can compute the new angle as, you compute what this vector will be. So this is the original angle plus pi. This would be the blue one. You want to minus 2 of these things. So that's the formula. anyway, it can be simplified into this, but you know, that's essentially what we need. So all the way from this, you know, they kiss, and then you have like two velocity, but technically when you are looking at this blue one, you don't care what that green one is. And so you can remove that green one. Now you have original angle, new angle. You want to compute that, a lot of math, whatever. In the end, you know that the new angle can be computed by 2 theta minus pi minus the original angle. And the original angle can be found by speed y, speed x, do the arctangent. This theta is like x2, x1, the two ball. You can also find it. So anyway, everything can be found. Just a lot of math, calling some functions. But in the end, you know, at least you can compute what they are. So that's essentially what's going on here. So if you look into the code here, that's essentially what we are trying to do. The three lines basically. So all of these, you know, you don't really care about all the computation. At the end, this is what you need: theta, original angle, and you will get a new angle. So this is the case: theta, original angle, and you will get the new angle by doing the same thing here: 2 theta minus pi minus original angle. 2 theta minus pi minus the original angle. So that's essentially what we done. Let me show you how it works. But this is basically what the code is. Okay, so another thing, so you will see that, you know, when you work with all the other ball, usually this other ball, if that is the same as the same ball, you don't really care. You don't want to collide with yourself. You will always collide yourself. It doesn't make any sense to do that. Now, if you want to see if they collide, then you want to see the distance. So like when two balls collide, meaning that their distance is larger, you know, their distance is smaller than 2 times the radius, or, you know, smaller than R1 plus R2. This even work when you have like different size of, you know, balls. So anyway, if the distance larger than size, then you return, basically meaning that their distance is far away. So they didn't collide. The size is the diameter. So 2 radius here. So you do nothing in that case. So otherwise, you would just move them. And then you want to see where they are heading to. You want to compute the new speed, where they are heading to. Cool. So this is a little bit tricky because you want to revert the ball back to where it was before the collision. So you first move the ball and you check whether they collide, and then you actually just don't do it. You revert it back to where before they collide, and then you apply the new direction. So there will be a tiny difference when the ball is moving too fast. That will be not realistic because, you know, you are calculating frame by frame. So this is like a necessary evil to avoid, you know, other weird behavior of the system. Cool. Anyway, this is what the code is like. It's actually not that messy as you might thought. This is the main file. So you have 20 balls. You initialize all of them. And this is interesting because you want to set others to all the balls. So you have an array of balls. And for each of these balls, you will initialize a new one, and you will set all the others as the whole array of balls that you can iterate over. For each of the for loop, you basically, for each of the ball, you basically move it, you check whether it hit the wall. If it hit the walls, turn it around. If it hit another ball, then, you know, change its direction. And within this, that's basically what we talk about, you know, move basically plus equals speed x plus equal speed y, not interesting. Check walls is basically what we've had previously. If it hit the wall, turn it around. Now the interesting part is like set others. So basically you will set others to all the other balls. Check collision is basically what we talk about here. You want to see whether you collide with one another. So you want to go through the for loop for all the other balls, whether they collide. For each collide checking, you basically do nothing if it's the same ball, compute the distance, and do nothing if they do not collide. Okay, now if they collide, you are sure they collide, then you want to revert the ball back to their original position rather than the new position, because the new position they are already collide. It's very hard to compute where they are going. So you move them back when they haven't collide. Now you compute all the velocity after the collision. Well, that's what you will get. So this is essentially what's going on. Well, a lot of things going on. Any questions on this? It's not that easy, but not that hard at the same time. It's like a lot of tricky stuff, especially like this revert back thing. The first time I'm trying to do this, I thought it would be much easier. But this seems to be the key. If you don't do this, there's will be a lot of ball that just stick together and they won't move. Because once they collide, all the computation will be wrong. So you have to tear them apart, and then you compute the new direction, assuming they will collide soon. And you apply that speed, sort of like, everything is like in this like frame by frame animation thing. So you can always think about, you want to move the next move. How do you predict the next move? But everything will be like discrete and quantized in some way. So a lot of stuff will happen where you have to take care about, you want to move it first or compute the direction first, then move it. So that's just the decision. And some of those are harder than others. Anyway, so what's going on here in each single frame is that, for each of the ball, you will move it, and, you will always check for all the other 19 balls, whether it collide with another. If it collides, then you have to compute where it's heading to. But think about it this way. It's like for each one single ball, there's just like tons of different walls around you. So to make things a little bit, easier to imagine. So this is your ball. Like for your for loop, there's a bunch of other balls. Some of them doesn't collide, but some of them are closer to collide that has a speed that's hitting you. So you can think about these as creating tons of different wall. And also you have the outside walls. So basically now you are moving these things around. So you will basically treat these as different walls. And if it hit the walls, then it will, bounce to another direction. So basically that's what's happening. So at each single frame, you have to go through all the balls, in this case, 4 balls. But for each of these balls, you have to check whether it collides with one of the 4 walls, but also whether it collides with one of the other 3 balls. And you have to do it for all the other instances. Cool. Anyway, that's how collision detection work. A lot of details, but the concept is not that tricky. Cool. So pretty much you can actually even make it more realistic. In this case, it's sort of funny because like, two things collide, they won't perfectly just remain their original speed. There will be some energy that's wasted. So the same idea of the decay thing for gravity is that now there will be some energy consumption. So the thing that we show here is called, elastic collisions, basically meaning that there's no energy wasted in this case. So where we talk about how we can do this, assuming all the mass is the same. So we didn't actually consider the mass. But when you want to think about the collision, when there's a mass, then technically there's like conservation of momentum. So basically, mass one, velocity one, mass two, velocity two will be the same as after the collision, mass one, the new velocity, m2, the new velocity. So this is like the conservation of momentum that will hold through for whatever collision that you have. For kinetic energy, basically, oh, I write it wrong. So forget about this. So basically, this is the kinetic energy. These two be the same as these, just with the original V1. So, by these two formula, you can actually compute the new V1 prime and V2 prime. That's how you can do it. But this is like assuming elastic collision, so there's no energy waste. You can also do it with 2D. 2D elastic collision, basically what we just go through. So what we just talk about is when the mass is the same, the two ball has the same mass or the same size. But basically you turn everything into a vector, and this is wrong somehow. Anyway, there's additional one because now things are much harder. You have to take care of angular momentum. Anyway, we won't go into details. For the case that we have here, this is good enough. These computation is good enough. But anyway, if you want to be realistic, then this is the way to go. You can, compute all the force, do all the simulation. There's also this collision with weight. I tried to implement this for a while. Anyway, it's working, which is good. Can show you what it looked like. Cool. It's kind of slow. Anyway, it's like two ball colliding with one another where there's weights going on. It's very hard to get it done. This is actually copied from, again, the example. But as you just saw that, the small ball hit the bigger ball, and, the bigger ball doesn't change a lot in its momentum, but the small ball will change a lot in its momentum. That's because when we compute the MV thing, usually the small ball will have more effect on its velocity change. Anyway, different weights and different speeds. Then you have to consider all the, things here. Basically, you just compute these two things, but also the angular momentum to compute those. So you have to solve the equations, basically. You can also do something like this, the reflection. This is another example code where basically you have a ground where it's just a bunch of like piecewise linear, basically a bunch of different planes in different angles, and you have a ball coming down. And for each of these, you just want to check which plane did this ball hit, and you want to apply the reflection to different slopes. Yep. Cool. Yeah, so technically what's going on is that, well, the ground is just initialized with a lot of like random widths and random slopes. Together, they will compose the whole ground surface. And there's this object, basically that's a ball, and initialized with a small x velocity and influenced by gravity, but at the same time collide with walls and grounds. So it will collide with one of those. Cool. Cool. Questions so far? That's basically, a lot of different ways to look at how things work. But anyway, a lot of equation solving if you real want to um, dig into how it works. Cool. And the last thing I want to talk about is particle system. This is again kind of advanced, but at the same time really fun. So this is like a simple particle system, what we meant by particle system. So a particle system is basically, think about it like tons of objects. So in this case, if you want to, mimic this behavior, what you want to do is, just thousands or, hundreds or thousands of these balls coming out from this single position. But basically you are doing this particle object. And so for each of these particle objects, so each one of these things, we call it one each of as a particle, and it will have started here with a random, y speed toward upward and random direction. So you can think about it like this is like a, I don't know, like a spring of life kind of thing. So it will just randomly send something at different upward position, and then you apply the gravity. So how to work is that, you will have an array or a list of particle object, and each of these objects will have these own effects, like being affected by the gravity. And interestingly, then it's like it has to phase out over time. Otherwise, your system will just shut down because there are too many obstacles. So particles system is basically just a bunch of objects mostly, but you have to make it sort of like an object where you have a bunch of objects within that single object. So, a particle system is basically just an array list of particle objects. So these things we didn't, explain in detail. Array list particle is a list of class, a list of objects. So you can create a list of particles in this case. But basically, you can allow us to store a variable number of particles. That's what we need. And you have to show all the particle objects at each call of the draw. Well, this is another case where you can do this firework thing. This is again kind of like a particle system. Can you imagine how this can be done? I sort of already show it. But anyway, what's going on here is that this firework object originally is just one single particle going upward, or not even a particle. We don't call it a particle. It's just something that's going upward. So you have an object that's going upward. Let me redraw it. Going upward, going upward, going upward. And because of gravity, it will be slower, slower, slower. And at some point, it will reach this, speed. So at each place, speed y originally would be negative, right? Up is negative. So originally it would be negative. And, at each single time you will do this, speed y plus equal gravity. So all the way until someday, this speed y would be positive. That's when it reached the top position, right? And so once it reached the top position, now you want to explode. So at that time, this firework object is kind of interesting because originally it's dynamic. Originally, it's just one single object, like one single tiny ball that go upward, 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 upward until the day when speed y larger than 0, when it reach the top, then it breaks into a bunch of particles. And now at this point, you just apply something before. Now we just do this. Basically, now you get to throw, thousands of stuff from this position in any different direction. So you explode. So you get, hundreds of particles that just explode at that point. So, firework is basically kind of the same as this, just that, the explosion is much larger. And you will have something that start from zero. So you throw something, and then once it reach speed y larger than zero, and then it explode into this. And this can be done by a bunch of particle objects. And each single particle object is just one single ball affected by gravity. So, things just get more complicated over time. But, basically you can do a lot of things by just composing some of the ideas we've talked about. And this is one of the, very tricky ones to look at. So, to dig into it, starts as one single particle object and initialize with random force up. So you initialize it with a random upward direction, but also y, x and y. And it will flies up with gravity, slowing it down. So gradually becomes lower speed, explode when speed reaches zero. And once explode, become many particle object after explosion, initialize with random force towards random direction, center at the position where explode, fall with gravity. And you can actually also apply this die after invisible on the canvas. So whenever y smaller than zero, then you can get rid of that particle to save some computation so that, your system. Imagine like if you are throwing like hundreds of fireworks at the same time, your laptop will die likely. So that's particle system. But particle system is just a complex system where each single ball are affected by the same idea. Cool. Anyway, we won't do this, but if you want to, think about it in midterm assignment, you could also try it. I mean, you can find some of the example codes on processing official website. Cool. Any questions on motion and physics? That's pretty much what we want to cover. Yeah, but a lot of these is like, I guess one interesting concept in visualization or I don't know, animation is that you don't necessarily want to mimic exactly what the real world look like. To think about like the solar system one, if you mimic exactly how solar system work, it will be quite boring if you look at the things. And also when you want to mimic the gravity, if everything is like inverse proportional to the square of distance, it doesn't look quite good actually. So oftentimes, in art or in creative coding, we just explore what's the best way to sort of like have that behavior, but sometimes you adjust a little bit, sometimes make it constant speed, sometimes make it not essentially, square root dependent, maybe, just linear, but it's sort of like tell the same story. Cool. Otherwise, I mean, tons of things that you could explore. That's sort of beyond the scope of this course, but should be fun. Cool. I mean, for the rest, there's just some more things worth knowing in processing, but I guess this is pretty much sort of the end of everything we want to cover in processing. And on Wednesday, since Wednesday, we will start digging into Max. It will be a whole new world on how you program for more real-time music and audio. You can also do image and video visual in Max, just that the whole concept is different. Cool. Before that, I think we could just go over some more things worth knowing in processing. These are, of course, optional, but to give you some more flavor of what processing offer. we talk about a little bit about, the shapes. And at some point you will be like, shapes is like too tricky to work with in processing. You have that, like the begin shape things. Actually, there's the object-oriented interface for custom shapes. If you want to sort of like get a stars that you can pass across your, reuse it again and again. And you don't want to write a class. Actually, P shape is a predefined interface for custom shapes. So you don't necessarily need to create yourself a new class to work with the shape. But you can just, initialize a P shape object. This is like a shape object, processing shape. So P, everything start with P is like a processing stuff. So this is how you create a shape. You create a shape and then you do begin shape, S dot vertex, S dot vertex, S dot vertex. You define 3 vertex and then you end shape close so that it becomes the close object. So once you're done with this, this is in the setup function. Once you're done with this S now has a definition. Now this S corresponds to this whole thing, this whole shape. So you can actually just do shape as 200, 200. It will draw from 200, 200 and start drawing this shape that you define. So it's sort of like make it easy. So it's sort of like do the translation, rotation stuff for you. But it's much easier if you want to think about this like a stamp. You create a stamp, you define what the stamp is. Now you can just stamp it everywhere on your canvas. So that's pretty much what you can do. You can also do something like this, S.rotate, which is pretty fun. So you have a shape and then you can do S.rotate, and you can rotate the shape around the same anchor point. Cool. There's a bunch more you can do. P shape. You can also load the shape from SVG and object file where you already define what the shape is. So this could be handy when you want to model like a 3D mesh, or you have a predetermined mesh of an object. Then you can load shape into that. You can translate rotate. Just we see here rotate. You can do all the transformation on top of that shape specifically. So now it's an object dependent transformation. You can also reset the metrics. So everything here will be S dot translate, S dot rotate, S dot scale, S dot reset metrics now becomes the object oriented interface of shapes. So that's also showcase what, the objectness of it is like. Yeah. So one thing about this is that, once you do the stroke, it doesn't actually affect what we have. So this is like FF0000. So this will be the red color, RGB, R will be FF255, G0, B0. So this is just pure red. But it doesn't change the stroke. This doesn't apply to P shape. If you want to do it, you have to do S dot set stroke. So now you sort of like get a sense what object oriented programming is like, where everything is scoped. If you do this is affecting the global scope, everything else, but now this shape S is already capturized into this object. So you have to do something within that object. So S does set stroke. So now you can set the stroke into red. So this is basically turn how you work with these shapes into an object capsulized way of doing stuff. Cool. So that's one thing. The other thing I want to talk about is dictionary. So this is sort of like a very advanced topic in data structure. So, only until you talk about hash map, you will talk about dictionary. But in this case, we don't really care how it works. We just want to know that it's something that you can use. So dictionary, if you work with Python, Python also has a very nice dictionary implementation. You don't technically need to know anything about how it's implement, but it's like fast lookup for the corresponding value for a key. So what does that mean? So dictionary is basically, dictionary like a library. You can query it with a key, and it will returns the corresponding value. So think about it like this is like the ISBN, and then you go to dictionary, you get the book. This is like the word, and you go to dictionary, you get the explanation, the meaning of the word. So you will have a bunch of different key, and whenever you plug this key, query it to the dictionary, it will just pop up with that value very fast. Actually, it's just in constant time. Anyway, there's a bunch of different dictionary you can use. Integer dictionary, float dictionary, string dictionary, but basically that's just do all sort of like different mapping. So you can think about if you want to create a dictionary where you want to store, I don't know exactly my cat 250. Likely not weight. Weight, I don't know, 50 something. Dog for 100. I don't know. Numbers of cats in your zoo, I guess. Number of dogs in your zoo. Number of bears in your zoo. I don't know. Does that make sense? But anyway, if you want to store some pairs of, values where you want to have like cat, you have a value 50, dog, you have a value of 100, bear, you have a value of 300, then that will be sort of the dictionary where it can help. So integer dictionary, what you can do is that, it's actually weight, pounds. Does it make sense? Anyway, integer dictionary, weight map, that's what our dictionary will be. So we will have like weight map, set cat 50, dog 100, bear 300. So that basically will create this, like a table-like dictionary in your data set where you will have key value, but basically you will have cat, it will map to 50, you will have dog, map to 100, you will have bear, it will map to 300. So dictionary basically just do this table mapping things for you. And if you want to query what, once you define this dictionary, if you want to query, you just do weight map dot get cat, then this will return the corresponding weight for that. So dictionary basically is just a table lookup that's very efficient. So you might wonder, this is fine. Why should we use this? It's like a lot of mess. We can already do it with an array. We can have string animals, cat, dog, bear, and we have weight 50, 100, 300. And basically you could just go through this, array. You just use a for loop to look up the key, go through all the animals. If animals I equal cat, then I just get the weight. Why? Why shouldn't we just do this? Thoughts? Imagine we have like 100 animals, thousands of animals.
Sorry, the question is like, why would we use this over a int array?
Why shouldn't we use this
Memory.
against dictionary? Yeah, so basically the idea is that what if, you are looking for bear and bear is the 500 ones. You basically need to go over the whole array to find that bear until that match. So the worst case scenario in this implementation is basically the length of your array, the length of objects. So that's not the case of dictionary. So dictionary actually has always O1, so constant time. The detail is something called hash map. We won't go into details, but basically this is slow compared to whatever you get from dictionary. Dictionary is like you always get constant speed when you get something from that. And it will be much faster, especially when your object happens to be much longer. And think about bear is the 100 one. Then you have to go through the whole array to just scan through to check whether there's a bear at the end. So basically, this is what hash map and the dictionary work. But basically, We won't go into details. But anyway, I guess there's no other ways I could explain. Just that, you have to go through the whole array to find a match. And that's the worst case scenario. And in the case of dictionary, you won't face that issue. Exactly how? Data structure will tell you that. But basically, hash map is the key, the idea behind that. And that's actually an extension to the dictionary idea. It could be anything to anything mapping. That's the funny thing about hash map. You can do object to object mapping. You can do any kind of key value data type if that thing is hashable. We won't get into details, but that's the idea. If you've implement something that's big enough, think about, you have a database with 1,000 entry, 1,000 different animals, then you will see the difference in dictionary versus this array lookup thing. Cool. So in this case, we talk about this hash map. We could also have a string to array hash map. So just to showcase how flexible the things could be. So you can actually map string to an integer array. So think about in this case, I don't know what these things would be, but imagine a case where you want to know, like whenever you want to draw a cat, maybe you need these three numbers to see where the cat's, foot or where their, I don't know, their locations are. So you want to store three number, 100, 150, 200. These three numbers for cat. For dog, you want to save this thing. For bear, you want to save this thing. So this is also possible using hash map. You go from a string to an integer array. So going from a string to integer array. And basically you do the same thing. Put cat like the key, and the value will be an integer array. So you can pretty much just do the same thing. Now you get an integer array when you do m.get. This is the hash map you get there. So it will return this, array back to this value. So now if you go through the value and you draw the circle, you see those four lines, four circles, basically 100, 150, 250, 300. So this just to showcase that, hash map can do any-to-any mapping. So declare a hash map that maps strings to integer arrays, set up the dictionary. This could be, a dictionary from a string to an array. Query the hash map, you will get the corresponding integer array back. Then you can just iterate over that. And if you print the things out, you will see that, it's basically cat equal the things. That's basically like an integer array at some position in your memory. Anyway, I guess we go kind of too deep into these things. But just to showcase, processing is actually built on top of Java. So a lot of things you can actually grab from Java. So hash map is something, defined in Java. So you can actually extend it, use it in processing directly, or, use processing as, plugin on top of Java or JavaScript if you're using P5.js. Cool. I guess that's too deep into the stuff. But I guess we could just go a quick recap, and that's pretty much what we have for processing. We talk about gravity, basically, speed x plus equal acceleration, and then location plus equal speed. So you apply acceleration on top of the speed, and then speed will apply to the location so that you get the second order acceleration thing. And it doesn't need to be, gravity that's constant. It could be dynamic, where all the acceleration points to your cursor, where your cursor is. So in this case, your cursor will have a constant drag from dragging the ball. You can also combine different forces. Basically, if you know how to compute the force, in this case, drag force would be F proportional to v squared, velocity square. And in this case, they will have different behaviors because, once you compute the force, even though it's proportional to velocity square, it F equal ma. So force will be the actual acceleration depends on the mass. So in this case, you will see how you can compute the combination force. And then we look at collision detection, how they collide, but basically you just want to check whether it collides with any of the other balls. And if they collide, you have to go through all these maths, but well, that's our formula. That's all we care, kind of. But basically the three lines basically just, all these mathematical, computation, all we care is that how you compute theta, how you compute the original angle. Now you can get a new angle by combining these two things. And that's the three lines here. Flow theta equal arctangent blah, blah, blah. Flow original angle arctangent blah, blah, blah. And then you get a new angle. And then you get the speed x and speed y by cosine, sine, whatever with the new angle. And that's it. Cool. So basically you just need to go through this for each single ball, check whether it collides with other balls and where they will be next. And we talk about all these things, but we didn't actually talk about it. It's just like the principle of these, but you have to calculate. But if you know how to calculate, how to solve the equation, then you can actually do these different ways with different speeds. And you see that when it collides, it will have much larger effects on the smaller object usually because of the physical laws. And we talk about particle system, where basically just a bunch of objects, pretty much. But more interesting is this firework thing. It started with one single particle, but when it reached the top, defined by having speed become positive. Initially, going upward, meaning that speed is negative, and all the way until the top, it will turns into positive. So when it reaches zero, it explodes, and it becomes a bunch of particles. But everything will affected by the gravity. But the idea is that they're like random, direction exploding. Cool. That's it. So next lecture is actually not midterm assignments showcase. On Wednesday, we will talk about get started with Max. That's a tricky thing. So Max is installed on all these machines. And if you want to get it, you can get 3 months trial on your laptop. But the tricky thing is that for your final project, you likely want Max. So I will suggest you to install or start your free trial until 3 months before the due date of final assignment. That will be a better choice. Yeah, so don't start your free trial too early unless you have 2 laptops. Yeah. Cool. So next Wednesday, midterm assignment showcase, demo in class. Cool. See you on Wednesday.